Okay, thanks a lot, Janek. Thanks a lot for the invitation. It's really a pleasure to be here, even if it's online. So indeed, what I will be presenting today is joint work with Ignacio Cirac and Daniel Malz. So this work is on arXiv, but still not published. So it's about quantum metrology. And probably many of you are more experts than me on the topic, but just a very brief introduction. I forgot to say, please ask me questions along the talk. I mean, I didn't prepare to be very long, so I'm happy to discuss along the way. So in very general terms, the idea of quantum metrology, say using photonic states, is that we want to estimate some parameter. Could be, for example, a phase of an interferometer. And for this, we prepare some photonic state. And then this photonic state acquires some information about the unknown parameter. And finally, we measure it. And this may be repeated a few times. And then, so that we have some statistics. And the idea is that from the measurements, so these xj represent the outcomes of the experiment. From these measurements, we make a guess of the real value of the parameter. So this is a so-called estimator. And basically we want this estimator to be as close as possible to the real value. So one could take, for example, this is the standard mean squared error that you look on average, given all the possible outcome of experiments, how far your estimator is from the real value. So there are some very well-known results about the behavior of this mean squared error. So one is that if we use classical states of light, here n is the number of photons of the initial state, and by classical one usually means coherent states that are easily prepared, but one could, for example, also think of uncorrelated state, or so sending one photon after the other. Then one gets this scaling of 1 over n of the number of photons. But if we use quantum states instead, one can get a 1 over n squared scaling. And this is the famous Heisenberg scaling or Heisenberg limit. So this is all very exciting, but of course there are important drawbacks that are by now well known. So one is that these quantum enhancements are very susceptible to imperfections. So for example, if your measurement devices are not perfect, or if you lose some photons on the way in the experiment, then these quantum advantages, they quickly disappear, or at least they become less relevant. So the kind of famous case is that of null states, where just by losing one photon, the state becomes useless. Okay, so you may get at the beginning, if you plot this mean squared error as a function of time, you may get at the beginning it behaves much better than coherent states, but it quickly gets worse. Now, if this doesn't happen with all quantum states, so you can still build states that are entangled, but that they are more robust to photon loss. And in this case, you still get an advantage. But in general, I mean, you lose the Heisenberg scaling. So this has been discussed in these papers, for example. Now, there is a second drawback that is, in practice, I would say even more relevant, which is that quantum states are just very hard to prepare in the lab. Okay, so if you take Fock states or vacuum skew states or null states, I mean, one can go at most to 10 or maybe 20 photons. So of course you may say, okay, why should I care to have a better scaling with a number of photons if I can just prepare coherent states of a much larger number of photons and do better interferometry? So okay, you may ask, when does quantum metrology become relevant in practice? And the usual answer to this question is that, well, it becomes relevant when the number of photons is limited for some reason. Okay, so a very famous example is gravitational wave detection, where if you were to increase the photon number, or say the photon flux, then this would create some back action on the measurement devices. So you want to, without increasing n, increase the measurement sensitivity. And this can be done by using quantum states, in particular using squeezing. So another example that it's, say, a more still not that directly applicable, but it's still a nice possibility would be in the measurement of delicate samples. Okay, so here you could think of a virus or even smaller biological or samples that could be easily damaged or destroyed when you by the photon flux, no? So let's say that after a few photons are absorbed, then they become damaged. So this is what I will be considering in this talk. And so to warm up, let's look again at these phase measurements, because in fact here there's been several experiments already. And very roughly speaking, the idea is that because you have this sample, this somehow changes the phase in this interferometric setup. And indeed you can, and here it's quite simple, right? Because the point is, if you put a constraint, so say, okay, this sample is destroyed after a few photons are absorbed. So you put a constraint on the number of absorbed photons that this sample can tolerate. So usually you expect that this number of absorbed photons will be proportional to your resource, so to the number of photons. So what this means is that, well, basically we can just recycle all we knew for a fixed n. Okay, so all these results about shot noise and so on, and directly apply them when we have a constraint, instead of in the number of photons, in the number of absorbed photons. Okay.
Can I interrupt you for a second?
Yes, yeah, of course.
Because here it's important distinction whether you talk about number of photons in this arm, in this upper arm where the sample is, or in total, yes? Because the absorbed number of photons is just in this arm, so it might not be necessarily proportional to n if you, for example, put most power in the lower arm and so on, yes?
Yes, it's a good point, yeah. So I was a bit too, yeah, I agree with you. I mean, I didn't think carefully about this scenario, but indeed you could play with this. So because you put the constraint on number of absorbed and not on n, you could think of strategies where most of the photons are sent here. And actually this could be interesting. I don't know if it has been explored or not. But, okay, but this thanks for the question, because it kind of motivates the fact that not always, if you put the constraint on the number of absorbed photons, is equivalent to putting the constraint on n. Okay, and you can kind of exploit this, and this is a bit what we do in our work, where we instead consider frequency measurements. Okay, so basically the idea is that you want to measure a parameter of a Hamiltonian. Okay, this could be a frequency. Now, in this case, it's well known that the number of photons is of course a resource, and also the number of repetitions, but also the time of the experiment. So the longer the time the experiment takes, the more information you can acquire about this parameter, which kind of makes sense, right? Because, then, for example, if you would look at this mean squared error or at the quantum Fisher information, you will see that this scales quadratically with time. Okay, so both the number of photons and the time are a resource. And indeed, in this case, it's a bit less clear how the number of absorbed photons relates to the resources, okay? And this was the first thing that we wanted to explore. And for that, we took the following scenario, okay? So these are a bit the rules of the game, like the metrological scenario that we consider in our work. So it's the following. So we imagine that we have many of such delicate samples. Okay, so it could be viruses and you can take many copies of them. This is not a limitation, but you take them sequentially. Okay, so you have a machine that you use to measure them, and you take one after the other. And in this machine, you also have quite a lot of freedom. So you can prepare any photonic state of n photons. I mean, n is not constrained. Okay, so you can take any n that you wish and any time that you want. But the constraints, I mean, they are indirectly, so the constraints that we put, one is the total time, which kind of makes sense. So you can measure as many as you want, but until you reach a total time, okay? And then you have to stop your experiment. So this kind of a global constraint. And then we also have a constraint on, for each sample, the number of photons that it can absorb. Okay, so because we assume that after this in general will depend on the time, on the number of photons, but we assume that, yeah, when it has absorbed a given number of photons, and the sample is damaged and destroyed, then you have to take the next one. Okay, so these are the two constraints, which indirectly, of course, also constrain here T and N. But in principle, yes, these are not constraints, okay? The number of samples or the number of photons. And this makes it different from previous works in similar setups. Now, let me explain how we measure this sample and this measurement process.
So Marty, can I interrupt you again?
Yes, for sure.
So you think about this different repetitions as if you prepare new samples every time, yes? Or
yes, exactly.
Okay, because if it was the same sample, then you could just define the total number of absorbed photons, and you would not need probably to specify this total time, no?
I agree, yeah. So it's a new sample. So it's like we would have viruses or something, and you can take many of them.
Okay.
So you take one sample, you destroy them, you take the next one, and so on and so forth. Okay, now how do we model the sample? So we take a toy model, okay? And it's a toy model that it's clearly inspired by, say, previous works in optical interferometry, because it's kind of very related to this, to an interferometer, yeah, but it's kind of a continuous version. So the idea here is that you have, say, two cavities, okay, two photonic modes, and they interact through this coupling, which is standard creation annihilation operator. And what we want to infer is this coupling strength G. Okay, so this maps very well to an optical interferometer. And the phase would be G times time, let's say. Okay, but anyway, you can just take this model. And now we also want to measure this idea that the sample absorbs photons, and this we do it by a standard Markovian approximation. Okay, so the idea is a bit that we put some photons here on the sample, and then the photons, they acquire information on G through this kind of unitary evolution, but at the same time they are also absorbed or decayed, if you want. And this is a standard Markovian decay. So that there is this kind of interplay, right, between the information that we are acquiring and also the photons that we are absorbing. So a bit the idea to make it more precise is this one. So we would prepare some photonic state with a given number of photons, then we let it evolve in time, and while it's evolving, photons are being absorbed, and this is just a simple exponential form. And so this puts a constraint, okay, on N and T, because there is a maximum number of photons that we can absorb. Then we measure. I mean, we may wait until the sample is destroyed or not, but at some point we measure. And then we repeat until the total time is reached. Okay, so this is the setup. And then we will compute the mean squared error, and we will focus in the limit when we have many samples where
Yannick, I think your mic is not working well.
My microphone?
No, Yannick wanted to ask a question, I think.
But can you hear me now, Martí, or no?
Yes.
So no, it was just observation, because this is evolution absorbing photons. So I understand this operators D in your master equation.
Yes.
They should be like a dagger. So somehow, it's not decay, it's absorption, no? Just to be sure.
Yes, but
okay.
Yeah, I agree. It's I see your point.
I think you made a typo. I just wanted to make sure that so the model is that you are absorbing in a Markovian way the photons as a time.
No, but I think there is no typo, but in the sense that so how we model it. I mean, it's kind of a toy model, but that you would have the photons say in the sample, but then they can damage or they can get absorbed in the sense of, so it's really kind of a decay. So that it's like you put some photons, okay, there, and then they may slowly decay or get absorbed, okay, and this is how we model the damage to the sample. So if you want at t equals 0, really the number of absorbed photons is 0, okay, or the damage to the sample if you want.
Oh, okay, but when t goes to infinity, everything is absorbed.
Yeah, and you have yes, exactly.
Okay,
so,
perfect.
So that's a bit the model, yes.
Okay,
I mean,
thanks.
it's a bit to picture this idea that you can damage a sample either by putting a lot of photons or by putting a few photons and waiting for a long time, right? You expect that they both time and the photon number will somehow damage this, and we model this by a simple Markovian process. Okay, so yeah, just to reiterate once more, so we have this picture where we measure repeatedly samples, and each sample is modeled by a simple two-mode system, and then we put constraints on the total time and on the number of absorbed photons in each experiment. So, just to be pedagogic, I put a few equations just to give an idea of how the results work. So in particular, let's look at the case where here you use coherent states. Okay. So indeed, the inverse, if you want the measurement precision, or kind of the inverse mean squared error, will be 1 over the number of samples that you measure and the Fisher information, I mean, say the classical Fisher information in each measurement. And this is just given by t squared, as I was mentioning before, times the number of samples that you've used to measure. Okay, so again, this decays in time. Okay. Now the point is that you can re-express this in terms of the constraints, so say the total time and the number of absorbed photons. So you use these simple equations to re-express say the classical precision in terms of your constraints, and then you maximize over mu, which is the only free parameter. So you maximize over the number of samples. And what you see is that this expression is maximized when mu tends to infinity, and then you get this result, okay? So the bottom line is that for coherent states, the measurement precision is given by this, is bounded by this quantity, which kind of makes sense, okay? So the precision grows linearly with the total time, and it grows linearly with the number of photons that the sample can absorb at most, okay? And it follows directly this result from the short noise limit. Okay, so it's a kind of short noise limit applied in this scenario. And what is somehow interesting is that this is obtained in this very particular limit, which we call the Poisson limit, which is a limit where you send the number of samples to infinity, also the number of photons that you use to measure each sample to infinity. And to keep these constraints fixed, you also send the time of each experiment to 0. Okay, so the total time and the number of absorbed photons are kept constant while sending the number of photons to infinity and also the number of samples to infinity. Okay, so it's kind of a theoretical result, but it's nice because it's really a classical strategy that it's very extreme. Okay, it's a classical strategy where you are using infinite photons at each run of the experiment, and you are measuring infinite samples, okay? But still, even if you are take this extreme limit, the amount of information that you get is finite, okay? So this is kind of a appealing fact of this scenario. And now we can look instead at quantum states and say now Martí? We put some, yes?
Yes, sorry to interrupt, just a question. So how do I interpret when I set gamma, do I understand correctly? If I send gamma to 0, I have no knowledge at all, right, in this limit? So that means that no photons...
No, on the opposite. So if you send gamma to 0, this goes to... sorry, yes, you're right.
This goes to infinity, no?
No, but that's what you want, no? Because this the inverse means...
this is the inverse, okay.
Yes. So it's kind of the measurement precision, yes.
So basically this means that when I absorb a photon, it doesn't damage anything, kind of, no? I mean, this gamma to zero limit is some kind
well,
of...
no, this is what it means, because the gamma is the rate of absorption.
Yes.
So basically, if you don't, what this is telling you is that if you don't absorb photons, of course, you can get infinite information. So you can send
Okay,
the
so this
error
constraint is not playing any role. So some kind of, I cannot burn the sample.
Exactly, yes.
Okay, good, thanks.
Yes. Yeah, this gives kind of a time scale of burning or of photon absorption.
Okay, thanks.
Yeah, so, okay, we have this bound for classical states, I mean, given the constraints, and then we can consider instead quantum states of n photons. And then one can show it goes kind of similar. So we, again, consider the limit of fast measurements. But since it happens that since we fix n, you do fast measurements, but not that fast, okay? So the time that you use at each run of the experiment scales like 1 over n. So if this n is of the order of 1 or 10, well, so is this time, okay? But still taking these fast measurements, you can show an expression like this, where basically what you see is that the quantum advantage, so if you divide this by the classical result, it scales as n over the number of absorbed photons squared. So this is telling you indeed that if the number of absorbed photons is small, then using photonic states of a few photons can do better than any classical strategy. And this F I will discuss later. So this F depends on the particular state that you are using.
Why, Marty, but why do you say consider quantum state with Heisenberg scaling?
Yes, well, if you don't take Heisenberg scaling, then it will not be proportional to n, but proportional to n to some power that is smaller than 1.
But on the other hand, we know that that in presence of loss,
you lose this.
We don't. The optimal states are not the ones that would give Heisenberg scaling without loss. So
yes, I will discuss this a bit more later.
Okay.
But okay, I agree with you. Yes, the point is this is so what we study here is going somehow a subtle limit, because you are sending the number of photons to infinity and also the time to 0. So I don't know exactly how to put it, but it's still a bit less clear what are the optimal states. Okay, but okay, maybe for the moment, I mean, I just wanted to give the rough result, and maybe later we can. I will come back to your question. And indeed, here I'm assuming states with Heisenberg scaling. Okay, but it could be that. Yes, I think it's in this case it's still true that Heisenberg scaling is needed to get the maximum precision. But okay, we can discuss this. But what I just wanted to say also is that you can upper bound this F. So again, you can use these results that are okay well known by Rafael and Janek also were involved in these works. So basically you can use these upper bounds that they are known for in the presence of photon loss. And this F, you can upper bound it by the number of absorbed photons. So this is the best case scenario using quantum states. Okay. So the quantum advantage will scale at most like n over the number of absorbed photons. Okay, so before I discuss this a bit more in detail, I just wanted to give an example, okay, of what's going on. So here what I'm plotting is the inverse measurement mean squared error. So again, you want this to be large. Then I'm plotting the classical bound over the number of absorbed photons, and this comparing to using twin Fock states of n photons. And I take this n because the number of absorbed photons is small. I also take this n to be small. Okay, so it goes from 2 to 10. And basically what you see that it's nice because even using twin Fock states of 2 photons or of 4 photons, you can do better than classical strategies where you are using, say, an infinite amount of photons. Okay, so you are using coherent states of arbitrary intensity. And this is kind of first main message of this talk, that it's kind of a well-defined scenario where few photon states do better than any classical strategy without constraints on the or at least without direct constraints on the intensity. Okay. Yeah, so it's kind of nice because when you also use these states of less photons, they are also more robust to noise. Okay. And as I was saying before, you need to repeat. I mean, this is kind of that you are measuring the samples many times. But okay, here I'm plotting the number of measurements that you need to do as a function also of the number of absorbed photons. And you can see that when you are at the order of 2 or 4 photons, you need of the order of 10 measurements. So this is really telling you that, say, 10 measurements on or 10 or 20 measurements on a twin Fock states of 2 or 4 photons, it gives you more than infinite measurements on a arbitrarily intense classical state. Okay, and the reason is just because we are putting this extra constraint on the number of absorbed photons. So it's really quantifying this intuition that when you have delicate samples, quantum states can do better than classical strategies. So, okay, you may be asking what's going on. So how is it possible that these Fock states do better than any classical states? And here it's nice to look at this Poisson limit that I mentioned before, where you send both the number of photons to infinity and the time to 0 while keeping their product constant. Okay, so in this case, if you take the quantum feature information for classical states, so the shot noise limit, so what you see is that this goes to 0, okay, because you get a scaling that goes like t squared times n. So when you take this limit, this goes to 0, which means that you don't get any information in 0 time, which kind of makes sense, okay? You send the time to 0, and then the amount of information also goes to 0. Instead, if you use quantum states, and that's why I before was saying that I was taking the Heisenberg scaling, it's nice because this limit goes to a constant. And okay, this is really a theoretical observation, but what is this is telling you is that if you use so if you use quantum states with Heisenberg scaling, essentially you can get a finite amount of information in 0 time. And of course, this is a theoretical observation, but in practice, what it means is that even if you put this n finite, and this t behaving as 1 over n, you still get something finite in a very short amount of time. So here, what we are exploiting is that the fact that when you send the t2 in the limit of fast measurement of fast processes, quantum states do much better than classical ones. Okay, so this is what we are exploiting for these advantages. So now let's quantify a bit more this. So now I go back to this f that I was mentioning before, that this f depends on each particular state. And also, okay, to Rafael's question about which states are better or worse. And basically what you can, so this, to compute this f, basically what I'm doing is I'm taking this limit where I send the number of photons to infinity and the time to 0. Okay, and of course taking into account the fact that you have mixed states and so on and so forth. And basically here are some examples. So this plot is really obtaining this limit, okay, when you send the number of photons to infinity. And you see how different states perform. So for example, here I'm putting noon states, twin Fock states. So you can see the noon states do very good for very small number of absorbed photons, and then they do worse. For example, twin Fock states, they do reasonably good. And so do squeeze states, okay? And this is kind of expected given previous results on how photonic states are susceptible to photon loss or to noise. And
Martí, can I interrupt you for a second?
Yes.
So because you are writing this Q Heisenberg as if there was no loss at all, yes?
Yes. Yeah, I mean, this is okay.
Principle, you should add like exponents to minus gamma n
Yes.
t, I guess.
Yes, you are completely right. So this, again, I was a bit too not rigorous, but even when you add this exponential that you are mentioning, then you get instead. Okay, I think I will need to check, but I think you get more or less the same. So this is what.
Yes, I mean you would get additional factor.
Exactly. You're completely right. You get an exponential here minus n absorbed, and this is the behavior for
because t is 1 over n.
Yes.
Okay, then it gives you a constant.
And this is exactly what I'm plotting for Nun states. So you get this n absorbed squared at the beginning, and then an exponential factor. Yes, here I just wanted to give the intuition. But indeed, as you are saying, I mean, this, of course, it's only true when the number of absorbed photons is very small. When you start having photon loss, then you get punished, okay? And it depends then on which state you take. And here, okay, we just checked some states that, for example, twin Fock states are known to be quite robust to photon loss, and this is confirmed here. But we didn't check the optimal states that you've considered. Okay, because it's a bit, at least to me, it was not that simple because we are taking this limit of a large number of photons. Okay. Yes,
but okay, but okay, I would be wondering. Okay, you are changing the constraints you have, but okay, in presence of, okay, so then it's not obvious. Okay, I agree.
Yeah, I think it's okay. At least for me, it's not completely obvious. But for example, what I can say is, if we use these upper bounds, then we get that this f is upper bounded by the number of absorbed photons, and this is upper bound. This upper bound, and this upper bound you can saturate it when you send the number of absorbed photons to also. They become very large, okay, because this is the case that is usually studied in the literature. But in this regime of, let's say, a large number of photons, but a very small, this Poisson limit, if you want, it's not so clear how these optimal states would behave. Okay, I think it's an interesting question to explore.
Because, okay, if in standard quantification of resources, if I have this model of loss you have, and I'm allowed to take time as short as possible and repeat everything as fast as possible, then I know that, for example, if I just use this Nun states or something, then I get basically the same as with single photon states.
You mean with coherent states?
Okay, I mean, because in some sense, if you have freedom to make time longer,
yes,
and if you had no losses, then whether you use Nun state or single photon state n times longer is the same.
Yes, but the problem is that you have losses, no? So it's
yes, and if you have losses, this changes. But okay, I know that the optimal states then perform better than Nun states by a factor which is more or less E, like 2.71.
Yeah, so I would expect that if you would take these optimal states in these plots, they would they would stay below this line, and they would saturate this line for large number of absorbed photons. And in this regime, I'm not sure how much better they would do.
Because I see that more or less this coefficient here between this black line and your purple line is like this factor E, more or less, no? Like 2 point something.
Yeah, it's a factor 1/2, no? Because I think twin Fock states they get 1/2 of this upper bound.
Yeah, okay.
So I think your optimal state would be somewhere here. Okay, I would get, I mean, it's a bit like squeeze states that they eventually will touch this bound. And I think the optimal state would be the same. In this regime, it's impossible because noon states are the best and they don't saturate the bound, but eventually they would hit it.
Okay.
Yeah. Okay, so and okay, now I wanted to also discuss the robustness to noise. So here we consider two types of errors that are also has been well studied in the literature, but we wanted to do a similar analysis, but when you change a bit the rules of the game in the sense that you put these different constraints. So basically here, what the sources of error that I consider are the detector efficiency. So here I'm plotting 1 minus detector efficiency. So here it means that I have a perfect detector. And as I increase this, I mean, there's a higher probability of photon loss. So here it would be 80%, for example, efficiency. What we also consider is the extra time of preparation and measurement of quantum states, okay? Because as I was saying here, we are interested in this scenario that we do fast measurements. So of course, you also need to take into account the time that it takes you to prepare and to measure the quantum state, which is something that is usually ignored, but is actually in practice because people use post-selection, or, I mean, it might take much longer than just using a coherent state. So this is this extra time multiplied by as I was saying, the rate of absorption, okay? So again, when this is 0, you have essentially you prepare it as fast as a classical state. And as you increase this, you have this extra error, okay? Now in gray is the region where I cannot get any quantum advantage with twin Fock states. And here I can use any state that I want of any number of photons, and still there's no way that I will get an advantage. So this already tells us that we need detectors that are at least 80% or 75% efficiency, and likewise for the extra time of preparation. What is interesting also in this setup, that this I don't know if it also appears in other ones, is that so here what I'm also plotting is different ends of different photon number. So I go from 4 to 64. And it's a bit the same, okay? So for example, in this curve for 4 photons, if I'm on the left of the curve, then it's possible to get in a quantum advantage. Otherwise, it's not, okay? And so as expected, so here if you have only 4 photons, I need detectors with a higher efficiency. And I need to prepare them faster than if I would have 8 or 16, okay? Now, if you would take the extra time to 0, then what you see is that in general, increasing the number of photons helps you in the sense that you can have the detector less efficient, okay? So it gives you more freedom in this sense. But what is interesting is that when you take both limitations into account, then it happens that photon states, or say 8 or 16 photons, they become the best. Okay, so here I didn't put it I put a constraint, the number of absorbed photons equals to 1. But then it happens that really, if you were to naively increase the number of photons that you are using because you want to get a larger quantum advantage, you also need better detectors and to prepare them faster, okay? So really, it's nice because the states that are more robust to photon loss are states here of 8 or 16 photons. And if you were to increase this, then it would become more stringent, okay? So, okay, we thought that this was also an interesting observation for this scenario. And so you can get similar plots, but for more general states. So here I'm using this general upper bound. So this would be kind of a best case scenario. And you see that, of course, then you can tolerate much higher efficiencies or inefficiencies and extra times. But okay, this is not clear if it's saturable or not. So one would need to again check these optimal states. So this is just an upper bound. And now I move to the second part of this talk and this project, and this is in fact how we began. So I don't know how I'm doing on time. Actually.
So you have 5-10 minutes.
Okay,
10 minutes.
I went very slow.
minutes.
It's okay, but okay, I can explain this. It's okay in 5-10 minutes. So here the idea is to use kind of, because we want to measure. I mean, this plot clearly shows that we want to measure and prepare quantum states in a fast manner. And so the idea is to use atoms, in particular atomic ensembles, to prepare and to measure photonic states of light, okay? So in particular, the focus here is really on this phenomenon of superradiance. So this is how I started working on all this. So we did these two papers before, and this was really our focus. And then these first results are presented, it was just something that we realized later. But okay, now I will quickly explain what's the main idea. So for example, here the main idea would be, so we want to prepare these photonic states, like these quantum states, N or Fock, in the cavities. And for that, we will use atomic ensembles, okay? So basically, and in particular, the idea will be, so these cavities are interacting through this interaction G, but now we will also couple them to these atomic ensembles. And this is a coupling that we can control. So I'm sorry, I'm calling it here G, it should be another letter, it should be J. Okay, so anyway, the coupling between the atoms and the cavities is of this form. So you have the free, the atoms, like the free Hamiltonian, and then you also get a global coupling. So between all the atoms and the cavities, okay? So when you lose an excitation here, you lose it in a global manner, and then this creates a photon into the cavities. So this is kind of a Dicke interaction or Dicke coupling that is well known to lead to superradiance and supraradiance, and that's what we want to exploit here. So let me first focus on the preparation stage. So here the idea is the following. Here we would first prepare the cavities in the ground state or in the vacuum states and excite all the atoms, because more or less we believe that exciting atoms is easier than preparing photonic states, okay? So we would, with a laser, excite all atoms simultaneously, and then we turn on this Dicke coupling. And then you would see something like this. So I'm plotting the probability to get k photons in the cavity, given, I guess, 50 atoms at the beginning. So you would start with a kind of Poisson process. Now, what is interesting is that if you look at the average photon number in the cavity with time, so you see that to get n photons, this is more or less the time that you need, okay? So this is the coupling, so it's 1 over the coupling. But what is important here is that you get also 1 over the square root of the number of atoms. What this is telling you is that as you increase for a fixed photonic number, so if you say you want to prepare 10 photons on average, as you increase the number of atoms, you can do this faster and faster. And this is really due to superradiance. Okay, so as you increase n, this process becomes faster. And then the idea of the protocol is that we let it interact for this time, and then we measure the atoms, because again, we think that it's easier to manipulate atoms than photonic states. So we measure the atoms, and basically what we know is that, say, if we get n minus k excitations, then we know there are k photons in the cavity. Okay, so it's kind of a probabilistic way to prepare Fock states. And then we will get, yes, and k photons here and m photons here. So it's not quite a twin Fock state, but a kind of probabilistic 2 Fock state. And then we let them interfere. And this is what I discussed at the beginning of the talk. And now it comes the measurement. And so here now we want to, again, use these atoms, but now to measure the photon number. And what we do is we again couple the cavities to the atoms, but now the atoms are prepared in the ground state. We again let them interact. I mean, it's nice because you can solve all this analytically, okay, in this limit of a large number of atoms. But anyway, you can show that this is the time that it takes for all the atoms to be reabsorbed. And the error that you have in this probability, so again, this time it gets shorter with the number of atoms. So again, you can do it faster and faster. You have a systematic way of speeding up this process. And the error also decays as you increase the number of atoms. Actually, this should be a squared, sorry. So it decays quite quickly. So if you have if the number of photons here is much smaller than the number of atoms, you really get a very good number resolved measurement. Okay, so basically by increasing the number of photons, we obtain reliable and fast measurement and preparation of Fock states. So this is the main idea of the implementation. So I didn't get too much into details. And then we see that we did several calculations for different number of atoms, and we see that we do better than the classical bound. Okay, and okay, these numbers, not this, but this, I mean, could be at the order of experiments. And with this, I go to the conclusion. So the first main point is that we identified the scenario in metrology where few-photon quantum states can overcome arbitrary classical strategies. Then we also characterize the resistance to photon loss and these extra times of preparation and measurement. And this kind of motivated a way to prepare and measure photonic states in a fast manner. And I suggested that superradiance is a possible interesting resource to be used in quantum metrology and quantum information in general. And with this, yeah, that's all. Thank you very much for your attention.
Thank you, Martí. That was really good. I think we're a bit over time, but we still have time for questions. So maybe let me wait a bit if someone raises the hand or unmutes himself, herself. Please feel free. However, meanwhile, I'll ask about your last slide. So this last slide, when you said about the implementation,
yes,
here the setup is the same as you discussed before. There is some fixed number of absorbed photons and so on.
Yes, exactly. So here we take the number of absorbed photons to 1. So basically, this is it's just a classical bound. And here I'm plotting the number of photons in the cavity. So you see that when you start having up to 4 photons, and you do better than the classical strategy. And we do it for different atomic numbers. So as you would increase the number of atoms, you get better preparation and measurement.
Okay. Any questions from the floor? Don't be shy. You can also write in chat. I think.
So if there are no questions, maybe I can ask something.
Yes, yes, please do.
Okay, because I'm still a bit confused.
Okay.
Why you get different results than we normally do? Because in a sense, in your model, the number of lost photons is always proportional to the number of total photons, because you have losses in both modes with the same rate.
Yes.
So it doesn't. If you fix number of photons, it doesn't matter which state you choose. The number of lost photons is the same.
Yes.
With fixed total number of photons.
Yes.
So changing states with the same fixed total number of photons doesn't change this number of absorbed photons. So it's just a matter of rescaling the number of photons to number of absorbed photons. And now when you consider, for example, this formulas for this classical state,
yes.
And of course you write that this one you had before, this t goes to 0, the t goes to 0, and then you write this formula for classical thing. Oh,
well, this was to give an intuition.
But in fact, if you want to perform optimally with classical state, you would not take t to 0.
No, let me then show these are the formulas for the classical state. I think this is a bit more precise intuition of what you are saying.
You would take time basically like 1 over gamma or something.
No. Okay, yes. So what you are saying is, if you fix the number of photons and you look at the optimal time with classical states. Okay.
Yes, but you take into account the repetitions like this.
Yes, that's the important thing, that I'm optimizing not this so what you are saying is basically I look now at the optimal time that would maximize this, and this would be of the order of 1 over gamma. If I was to maximize the Fisher information, but I'm not maximizing the Fisher information. What I'm, sorry, it should be corrected. But what I'm maximizing is the number of repetitions times the Fisher information.
Yes, but this would...
And then you can prove that with classical states, the optimal strategy, given these constraints, is to take time to 0 and the number of repetitions to infinity.
Okay, but okay. I have to check it myself. Okay, but this is something I still don't see why it's. So
I have an intuition that maybe this is what helps you, Rafael, confuses you even more. Am I wrong? I have the intuition that I always thought in our results that somehow if I increase the number of photons, I also increase the amount of loss because the loss is related some kind of per photon. No?
Yes.
Because these are independent channels. No?
Yes.
And now somehow, when I start increasing number of photons, I cannot do that because I have a constraint. I cannot hit and go up arbitrarily because an absorbed is constrained.
So you see, you have to also decrease the time.
Time, exactly. So meanwhile, I'm decreasing the time, and this is what's happening. But then on top of that, by decreasing the time, I increase the number of repetitions.
Exactly. So there's a trade-off, and this trade-off is optimized in this limit when you send the number of repetitions to infinity and the time to 0. Even if, of course, individually it's non-optimal. When you added them up, all of them, then this is the maximum.
Yes. So somehow in that limit, it's because this amount of loss is not that important. Some kind of n is not necessarily going optimal to be very high. It's good to use states that are Heisenberg scaling, but not. Okay, this is very hand wavy, but.
Well, it will depend on the number of absorbed photons, what are the optimal states. And I expect they will be very much related to what you considered in the past.
Okay.
Okay, so maybe it's true what you are saying, but I would have to calculate it myself to convince.
No, of course I'm happy if you have comments. So maybe it's not true, but okay. At the beginning we were also surprised, if I may.
Okay, maybe.
So Ignacio also didn't believe me, but eventually he did.
Okay, then maybe I'll be waiting for questions, but you went really fast on this setup, so I'll ask just question about the setup. So maybe someone, because this is interesting. So yes. You use the atoms to prepare the input state somehow, no?
Yes.
Because the excitations in your harmonic oscillators is some kind of your input state. So okay, maybe like this for everyone.
No, sorry, the excitations in the atoms are.
Yeah, excitation in the atom, but then you couple it, you get the
yes.
excitation in your harmonic oscillator, and this is the state that gets absorbed and.
Yes.
Okay. So in real experiment, how would that work? These are these fibers with atoms that you.
Well, here it would not. I mean, we first considered with. Yeah. So we. Sorry, you meant no, not with a wave idea.
Yes,
okay,
so
I know less.
Just give us some intuition, like what would be this experiment that could do that? I mean, for everyone to know what are these type of experiments. No, this would be good.
Yes. Yeah, I guess. Okay, so here it was more Daniel Malz, the expert, but he basically checked, for example, for superconducting qubits, and that it seemed that it could be a good setup to perform this. But yeah, I don't know. I'm really not an expert on okay. Which could be a good implementation and how much this number of, for example, atoms can be pushed while still keeping this global interaction. And yeah, okay, so it's a good question, but.
Okay, so the key is that they need to all couple together in a coherent way to this oscillator. Exactly. Okay, this is the key of the system. Okay.
Yes.
So let me wait for some more questions. One last question, and otherwise I think we close.
Yeah. Absolutely.
Anyone from the floor, ladies and gentlemen? Well, I think it's the time then. So, but thank you, Martí, once more.
Yeah, thank you.